Welcome back. It's now the 14th lecture of the condensed matter course. More or less, we finished talking about scattering. There's a couple of little bits and pieces of scattering that I'm going to try to pick up later, maybe at the end of some other lectures. Instead, I'd like to move on and use what we've learned when we studied scattering in order to go back and study other types of waves in crystals. The type of waves we were interested in originally were electron waves and vibrational waves, or phonons. So let me remind you of a few things we had learned about electron waves in one dimension, and then we're going to try to generalize up to higher dimensions from what we've learned. So let's recall the tight binding model. Tight binding model for electrons, binding model in 1D. In 1D, and we're going to consider the case of two orbitals with two orbitals per unit cell, orbs per unit cell. And that can be two atoms, one orbital on each atom, or it could be two orbitals on the same atom, one atom per unit cell. And we can draw the dispersion in reduced zone scheme. Here's K, here's energy, here's pi over A, here's minus pi over A. That's the Bron zone, BZ for Bron zone. We can draw the dispersion kind of like this and like this, two modes at each wave vector K in the Bron zone. Or we can unfold that picture in the extended zone scheme, looking like this. Here's K. Here's pi over A. Here's minus pi over A. Here's 2 pi over A. And here's minus 2 pi over A. So we have the same picture for the first mode. And then for the second mode, we're going to shift things over, shift the thing on the left over to the right by 2 pi over A to make it look like this, and shift the piece on the right over by 2 pi over A to the left to make it look like this. So we have what we call the first Bron zone here, first Bron zone, BZ, here. And then these pieces here were the second Bron zone, second Bron zone, BZ. And so it's useful, there's K equals 0 right in the middle, it's useful to try to generalize this concept to 3 dimensions or higher dimensions. So let's do that. So generally, the Bron zone, since we're thinking about electrons in 3 dimensions, is going to be always defined as a unit cell in reciprocal space. And we're going to have to figure out what we mean by first Bron zone, second Bron zone, and so forth. So it's a general nth Bron zone, general nth Bron zone we define as follows. So we'll start with the first Bron zone. Points in K space that are closer to K equals 0, than to any other reciprocal lattice point. Lat point are the first Bron zone. First BZ. So all these points in the first Bron zone are closer to the point at K equals 0 than to the other reciprocal lattice points. Here's a reciprocal lattice point here at minus 2 pi over A. Here's another reciprocal lattice point here at 2 pi over A. And everything between minus pi over A and pi over A constitutes the first Bron zone because it's closer to K equals 0 than it is to any other reciprocal lattice point. This definition might look a little familiar to you because, in fact, it's the same definition as the Wigner-Seitz cell. So this equals the Wigner-Seitz cell of the K equals 0 point of K equals 0 in reciprocal lattice. Does that sound familiar, I hope? All points that are closer to a given reciprocal lattice point than to all points that are closer to a given lattice point than to any other lattice point constitute its Wigner-Seitz cell. So all points that are closer to k equals 0 than to any other reciprocal lattice point constitute the Wigner-Seitz cell of the k equals 0 point in reciprocal space. Good? Yes? Okay, good. So how about the second Bron zone? Points where k equals 0 is the second closest recip lat point. Lat point are the second Bron zone, are the second BZ. So for example, if we pick a point here, x, call this point x, the first closest reciprocal lattice point to this point x is here. The second closest reciprocal lattice point to the point x is k equals 0. Therefore, this point x is in the second Bron zone. Good? Okay, that's the definition. So a couple of notes about these definitions. First of all, one, Bron zone boundary to opposite BZ boundary is a reciprocal lattice vector, is a recip lat vector. Recip lat vec. Let's see. So here's a Bron zone boundary. It's the boundary between the first Bron zone and the second Bron zone, minus pi over a. Here's another one. It's the opposite one from minus pi over a to plus pi over a. Distance between them is 2 pi over a, which is indeed a reciprocal lattice vector. Similarly, here's a boundary between the second Bron zone, and out here actually would be the third Bron zone. And so it's a Bron zone boundary. The distance from it to the opposite Bron zone boundary over here at plus 2 pi over a is 4 pi over a, and that is also a reciprocal lattice vector. That is generally a true statement. Okay? There's a similar, so 1a, sort of a caveat, a corollary of this, is that BZ boundaries, or maybe it's not a corollary, but it's almost equivalent statement. BZ boundaries are points where absolute value of k equals absolute value of k plus g for some g, for some reciprocal lattice vector g. Okay? So for example, you need to have k and k plus g. Let's see, what is it? K and k plus g having the same magnitude for g being some reciprocal lattice vector. So if you take minus pi over a, you add a reciprocal lattice vector, 2 pi over a to it, you get plus pi over a. Those have the same magnitude, so you're on the Bron zone boundary. Similarly, you take minus 2 pi over a, you add a reciprocal lattice vector to it, 4 pi over a, you get to plus 2 pi over a. That has the same magnitude, so you're on a Bron zone boundary. The second statement, which is important about Bron zones, is each BZ Bron zone has the same area, or volume in 3 dimensions, same area, and represents each k point, each crystal momentum, each crystal wave vector, I guess, wave vector k once. That was our general idea of constructing the Bron zone in the first place, that every physically different wave is represented exactly once in the Bron zone. The second Bron zone is equivalent to the first Bron zone. We've just sort of moved the pieces around into different places, but each wave vector k is represented exactly once inside each Bron zone. Incidentally, is it obvious from the second Bron zone that you would define the third Bron zone analogously, points where the k equals 0 is the third closest reciprocal lattice point would be the third Bron zone. So you have the first, second, third. You can have as many Bron zones as you want. The final statement, which is useful, I think this is a homework assignment on the third homework set, that the number of k states, we even proved this in lecture, in each BZ equals the number of unit cells in system. In system. Does that sound familiar? We proved this in one dimension. I think for homework you're supposed to prove it in 3 dimensions. It is also generally a true statement. So actually let me do an example of this in 2 dimensions to make this more clear. So we're going to start with a square lattice in real space. The reciprocal lattice of a square lattice is also a square lattice. So I've drawn a square lattice. This is supposed to be the reciprocal lattice, so it's a square lattice again. I've colored some of the points differently just to make them easy to talk about. The point at k equals 0, I've colored black in the center. And so first we're going to try to construct the first Bron zone. That is the Wigner-Seitz cell of this black point in the center. So how do you construct the Wigner-Seitz cell? You put down perpendicular bisectors to the nearest points. Perpendicular bisectors to the red points here will make this point. That's a perpendicular bisector here. Then this plane, this perpendicular bisector, these two also giving all the perpendicular bisectors to the red points. And then you color in the area. That is the first Bron zone. Okay? Now, the distance across the first Bron zone is 2 pi over a, which is a reciprocal lattice vector, the way it's supposed to be. That distance there from perpendicular bisector to perpendicular bisector is a reciprocal lattice vector. Now, let's look for the second Bron zone. How do we do that? It's a very similar construction. You just start putting down more perpendicular bisectors. So here, the second closest sets of points are these blue points here. So let's put down perpendicular bisectors to those, like this, like this, like this, like this. So these are the perpendicular bisectors to the blue points out here. We'll color in the walled-off area blue, and this is now the second Bron zone. Now let's just check that it fits the definition. If you pick a point like here in the second Bron zone, the first closest reciprocal lattice point is this red point here. The second closest reciprocal lattice point is k equals 0. Therefore, this point here, somewhere in this blue region, is in the second Bron zone. Good? Okay. Now, it may not be obvious that the distance across the Bron zone from Bron zone boundary to Bron zone boundary here is a reciprocal lattice vector, but I'll show you that it is. This is a reciprocal lattice vector from 0 to the blue point. You just shift it like that. It's indeed the distance across from Bron zone boundary to Bron zone boundary. So we can keep going on, looking for the third Bron zone. And to construct the third Bron zone, we have to put perpendicular bisectors to these green points. So let's do that. Put down those green lines, which are perpendicular bisectors to the green points, and we fill in the area now green. And let's check that it satisfies the definition. If you pick a point here in the green area, the first closest reciprocal lattice point is this red point here. The second closest is the blue point out here. The third closest is the k equals 0 point in the center. So this is in the third Bron zone. Now, also, the distance from Bron zone boundary to Bron zone boundary across the system is 4 pi over a, which is also a reciprocal lattice vector. Now, another thing that you've been promised from these definitions is that each Bron zone has the same area, it looks like they kind of might, and that they should each represent each k point once. So the Bron zones represent every possible k point exactly once. To see this, what we're going to do is we're going to take the pieces of this puzzle and with some very crude animation, we're going to move them by reciprocal lattice vectors and show that they're actually the same shape. So let's see how that works. So I'm going to take this red section, the first Bron zone, and I'm going to get that exact same shape of the first Bron zone, same area, same shape, exactly by moving these pieces of the second Bron zone over. So this piece I'm going to move by a reciprocal lattice vector, like that, 2 pi over a over. Then I'll take this piece, I'll move it 2 pi over a over this way. And I'll take the top piece, move it 2 pi over a down, and the other one 2 pi over a up, and it fills exactly the first Bron zone. So, well, okay, my animation skills are not perfect. Wait till you see the other one, it's even worse. But you get the picture that it's supposed to fill the first Bron zone exactly once. And we didn't, by shifting things by 2 pi over a, we actually didn't change the waves at all, because if you shift by 2 pi over a, you're getting back exactly the same crystal momentum, the same physical wave by doing this. So the second Bron zone is effectively exactly equivalent to the first Bron zone. Now let's do the same thing for the third Bron zone. We'll shift this over by 2 pi over a, this over by 2 pi over a. Okay, now it's really going to get bad, but you get the idea that it's supposed to fit perfectly, and had I been better with my animation skills, it would have fit perfectly. Okay, so that's the general idea of Bron zones. Just a couple facts about Bron zones in 3D. So in 3D, the lattices that we're interested in, let's write down a list of the lattices we're interested in, or mainly interested in. We have simple cubic, we have BCC, and we have FCC. So the corresponding reciprocal lattices, reciplat, is, well, a simple cubic lattice has a reciprocal lattice which is also simple cubic. The BCC lattice, this is something I mentioned, and I think it's a revision homework problem. The reciprocal lattice of a BCC lattice is FCC, and the reciprocal lattice of an FCC lattice is BCC. So the shape of the first Broughon zone, first being BZ shape, is, well, for a simple cubic lattice, the Wigner-Seitz cell is a cube. So the first Broughon zone for the simple cubic lattice is a cube. For the BCC lattice, the reciprocal lattice is FCC. So we get something that's the shape of the Wigner-Seitz cell for FCC, which was a funny shape. It was a truncated octahedron. I'll show you a picture in a second. And for FCC lattice, the reciprocal lattice is BCC. And so you get the Wigner-Seitz cell for BCC here. Actually, I may have said this one is the truncated octahedron. No, this one's the truncated octahedron, and this is the, let me just show it on the slide. OK, so this is the first Broughon zone of an FCC lattice. This one's the truncated octahedron. This one's the truncated, dodecahedron. This one has 12 sides. This one has 14 sides. All right, whatever. These are the shapes of the Broughon zone. So in this case, the FCC lattice has a reciprocal lattice, which is BCC, and this is the Wigner-Seitz cell of the BCC lattice, and this is the Wigner-Seitz cell of the FCC lattice, which is also the first Broughon zone of the BCC lattice. Now you'll notice that these pictures are drawn in K space, Kx, Ky, and Kz, and you'll also notice that there are some letters dropped onto these pictures. These letters are there because people typically, when they describe points in the Broughon zone, they usually say, we're talking about the gamma point or the x point or the L point. And that's just shorthand nomenclature that you don't need to know. But it's worth knowing that they have these, when they say x point, they mean some particular point in the Broughon zone. So the point in the middle of a square face is called the x point, this point, this point, or this point. The point in the middle of one of the hexagonal faces is called the L point. The point in the center is always called gamma. You don't need to know these things. All right. So now that we have these pictures of the Broughon zone for our various lattices, we can start thinking about the excitation spectra, either the electronic excitation spectra or the phonon excitation spectra, for various different crystals. And so everywhere in the Broughon zone, there will be different, like in the reduced zone scheme, you'll have different excitation modes at each possible value of k in the Broughon zone. So let's do an example. Being that it's Valentine's Day, happy Valentine's Day, everyone, is we're going to do diamond. Yes, all right. Well, we do diamond every year, so it just happens to be a Valentine's Day this year. So diamond, you'll recall, is an FCC lattice with a 2-atom basis, 1 carbon at 0, 0, 0, and 1 carbon at 1 quarter, 1 quarter, 1 quarter. This is the shape of the Broughon zone as we had on the previous slide. Now the first question, and opportunities to win chocolate, how many phonon modes should there be at each k vector in the first Broughon zone? How many phonon modes?
1.
No.
2. 3.
No.
10.
No. Oh my gosh. So there's 2 atoms in the I'm going to eat this one myself. All right. I'm going to gain weight this year. No, there's 2 atoms in the primitive unit cell. Each atom can move in 3 possible directions. So that means you have 6 modes. Yeah. So let's see if we have a picture of it. Yeah. So here's a picture of the diamond phonon spectrum. So the way it's drawn is that you take cuts through the Broughon zone along certain directions that you're interested in. So for example, this line, so here's the frequency vertical, and then the k vector is horizontal, but this given to you in a cut. So this is cutting from gamma to x along the 1, 0, 0 direction, gamma to x along 1, 0, 0 direction along this dotted line here. And then from here to here is gamma to L along the 1, 1, 1 direction, from here to here along that dotted line. This one's a little more complicated. It's x to gamma along the 1, 1, 0 direction. So that actually goes from this x through this k into the gamma in the center of the next boron zone over. So that one's a little complicated, but all right. Now, you'll notice that if you pick a point in the center here, you will count exactly 6 modes, 1, 2, 3, 4, 5, 6. If you count over here, you'll discover there's only 4 modes. Why is that? Well, the reason is because 2 of them are degenerate. You'll see these 2 modes coming in to this point here, and then they have the same energy all the way down from here to here, and then 2 modes here are degenerate up here, and they have the same energy or same frequency all the way over here. And the reason for the degeneracy is because you're looking along a particularly symmetric direction where vibrations transverse in this direction and vibrations transverse in that direction look identical. Whereas along this direction, it's a very unsymmetric direction, so all directions of vibration actually have different energies. You can see a couple interesting things in this figure. The gamma point is k equals 0. You can see the acoustic modes coming down to k equals 0 linearly. And these are the optical modes up here at high frequency. And one of these modes is longitudinal. 2 of them are transverse. Now, we can ask the same questions about an electronic excitation spectrum. And when you calculate an electronic excitation spectrum in, say, tight binding approximation, you have to decide how many orbitals you're going to consider on each atom. So, for example, in that picture up there, we considered 2 orbitals per unit cell. So given that, a typical type of calculation for carbon, you don't want to keep all the orbitals out to infinity. So generally, you just keep the orbitals you're interested in. What one is usually interested in is the orbitals where there's some sort of interesting action going on. The one orbitals, those are core orbitals. They're just completely filled, nothing interesting going on there. The orbitals that are 3s, 3p, and so forth, those are just completely empty, totally uninteresting. The ones that are interesting are the ones that are sort of partially filled, partially empty. Those are the 2s and the 3,2p orbitals. So given that we're considering the 3s and the 3,2p orbitals, how many excitation modes, eigenvalues, should we find at each k point in the boron zone? One more chance. We're considering 4 orbitals per atom. What was the answer? 8. Do you say 8? Yeah, okay. So, almost got there. All right, 8. Yeah, so there's 2 orbitals per. You count, what you need to do is you need to count the total number of orbitals per primitive unit cell, and that will give you the total number of excitation modes per k vector. Now, this diagram, this is an excitation spectrum, an electronic excitation spectrum of diamond. These things are frequently known as spaghetti diagrams for obvious reasons, because it looks like some sort of complicated bowl of spaghetti that you can't make any sense of. But it's actually, it's fairly simple. Well, not that complicated. Again, you're looking at cuts through the boron zone. So this is a line between the L and gamma point along this dotted line. This is a line from gamma to x along this dotted line, then x to k, k to gamma. So it's basically just taking cuts through the boron zone. And at each k point, there are 8 modes. 1, 2, 3, 4, 5, 6, 7, 8. And in some directions, it looks like there's only 6. Let's see, for example, this direction, 1, 2, 3, 4, 5, 6, because 2 of them have become degenerate here. See, these 2 came together. Oh, no, hang on. These 2 came together here to make only 1. That's because there's actually 2 modes with the same energy, so you have to be a little bit careful about that. Now, carbon has a valence of 4, which means each carbon donates 4 electrons. And that means with 2 carbons per primitive unit cell, we have donated 8 electrons total, so you fill the bottom 4 bands with both spins. So the bottom 4 bands are filled, then there's a gap, and you have the upper 4 bands. And in fact, as we'll discuss in a couple lectures later on, that means what we have is we have a really good insulator, filled bands, then a big gap, and then a bunch of empty bands. It's also what makes diamond nice and transparent, so it makes diamond beautiful, appropriately enough for Valentine's Day. All right, so let's move on from here. I think that's enough of diamond for today. So one of the things that's fairly important about this story is that with our tight binding spectra, we always have the principle that if you take k to some k plus g, you get back exactly the same wave. And you have the same principle for vibrations as well. Now, you might ask whether this principle that if when you shift k by a reciprocal lattice vector, whether that is actually special to the tight binding approximation we used, or whether this is actually a general statement. Let's remind ourselves why it is that we found this for for a tight binding model. Basically, the tight binding wave function, this is in a slightly different language than I wrote it before, but you can write it as e to the I k dot r times electron sitting on lattice point r. We used to call this thing phi, and we gave this no, I think it's more or less. I guess the difference is now we're doing it in 3 dimensions rather than 1 dimension. That's why it looks a little different. But this is basically the tight binding wave function that we wrote down before. And this thing is obviously invariant under taking k to k plus g, because e to the I g dot r, when you shift k by g, e to the I g dot r equals 1, because g is in the reciprocal lattice and r is in the direct lattice. So if k gets shifted by g, it doesn't change this factor here, and you get back the same wave. So, but you might ask whether this is just a property of the tight binding model, or if this is actually something that's general. And this is actually a really important question, and it's a question that came up very shortly after the discovery of the Schrodinger equation. Schrodinger discovered his equation in 1926. In 1928, that people were already worried about this issue, and it was resolved very famously by Bloch, Felix Bloch, and what's known as Bloch's theorem. Bloch's theorem, all right, okay, which is frequently referred to as the underpinning of all of material science. It's an underpinning of all of semiconductor physics. It's an extremely important principle, which may not seem so important until we talk about some of its implications. But let me state the theorem first, then we'll prove the theorem, then we'll talk about some of the implications. So the statement is an electron in a periodic potential, periodic V of r, I guess periodic means V of r equals V of r plus V of capital R, with capital R being a lattice vector, has eigenstates of the form, okay, there's a lot of symbols here for a second, psi sub k of r equals e to the I k dot r times u superscript alpha sub k of r, where u is periodic. So it's the same if you shift it from u of r equals u of r plus r. And k's can be chosen in the first Brillouin zone, In other words, k is crystal momentum, k is crystal wave vector, This form is known as, this form of psi, is known as a modified plane wave, a modified plane wave that should be fairly obvious. It's a plane wave e to the I k dot r, and is modified by being multiplied by a periodic function u. That's the modification of the plane wave. The index alpha is the band index. And the band index is meant to describe, you get a different wave function if you're talking about this point here or this point here at the same k vector. At the same k vector, you can have more than one eigenstate. So the eigenenergies are E superscript alpha of k. So E1 and E2, depending on which band we're talking about, which energy level, the lowest or the next lowest or the next lowest, and so forth. Okay, so this is a pretty big bunch of statements we've made here, but it's fairly important because it tells you about the general structure of eigenstates in a periodic potential. So let's first prove this theorem, and then we'll talk about why this theorem is so important and why it underlies so much of material science and semiconductor physics and so forth. So first, okay, so this is sort of a quasi-proof. It's actually fairly rigorous, but we'll sort of not fill in the details. But the quasi-proof goes like this. First, we'll consider a Hamiltonian, which is H naught, just the free electron Hamiltonian, plus our potential V, which is periodic. So V is periodic. And H naught is the usual p squared over 2m. Now, if we threw away the periodic potential, we would know the eigenstates. Those are just plane wave eigenstates, plane waves. E naught, k, k, where E naught of k is just the h bar squared k squared over 2m that we usually have. So far so good. We know we have the plane waves. Then we have to add the periodic potential. Now, what can the periodic potential do? The periodic potential can scatter you from some k to some k prime via a matrix element of this form. Now, we know a lot about matrix elements of this form from what we learned in scattering theory. This thing here, this matrix element from a plane wave k to a plane wave k prime via a periodic potential v, is the Fourier transform of v of r, evaluated at k minus k prime. And that is the following. It is 0 if k minus k prime is not a reciprocal lattice vector, is not equal to g. And we'll call it v sub g if k minus k prime equals g. I'm going to call it k prime minus k equals g. That. And this is just Lowey's condition, that you can scatter from a wave vector k to a wave vector k prime only if the difference between k and k prime is a reciprocal lattice vector. We learned this when we studied scattering of X-rays and neutrons and so forth. So this gets us almost to the proof. So we can almost conclude the result here. Why? Well, the point here is that the Hamiltonian with the scattering potential is block diagonal, no pun intended, block diagonal, block with a K, diagonal. And what I mean by this is that you can scatter from k to a k prime if k and k prime are separated by g. And then from k prime you can scatter to another k double prime if those are separated by a g. And you can scatter to another k prime and so forth and so on and so forth. But you can never change the crystal momentum. All of the k's that you can get to by scattering via the periodic potential, all of them differ from each other by reciprocal lattice vectors. So the Hamiltonian breaks up into these sectors, if you like. And so the wave function must be of the form, psi k must be of the form, sum over g of some coefficients, let's call them a of g plus k, times e to the I k plus g dotted with r. Now, why should it have to be of this form? Well, you start with some e to the I k dot r. And then you mix into that, the Hamiltonian mixes into that different plane waves whose wave vector k differs by a reciprocal lattice vector g. And you can mix in as many of those as you want, and they all get some coefficients a. But at the end of the day, the wave function must be a sum only of things that have the same crystal momentum, k plus some reciprocal lattice vector g. There's no way the periodic potential can change your crystal momentum. That's the important realization. Good? Yeah? Happy? Good. All right. So from here, we're pretty much done, because you can just factor out the e to the I k dot r, and then you have sum over g of a of g plus k, e to the I g dot r. And this piece here is the periodic function u, u of r, which, and you can tell this thing must be periodic, because if you take e to the I g dotted with r plus r, move it by a direct space lattice vector, this thing is the same as e to the I k dot r. So this thing is periodic, as claimed. Okay. Furthermore, we can also check what happens if you take k and you shift it by a reciprocal lattice vector g. So let's actually take this form of k up here, and let's shift k by g, psi of k plus g. Actually, I've already used the letter g, so let's call this g prime. Shift it by k to k plus g prime. So we'll write it as sum over g, a sub g plus k plus g prime, e to the I k plus g prime plus g. But this sum is over a dummy index, so we can define a dummy index, let's call it g twiddle equals g twiddle vector equals g plus g prime vector. And then if you substitute that in, that becomes sum over g twiddle vector a of g twiddle vector plus k e to the I k, dot r, k plus g twiddle vector dot r, which is exactly the same expression that we started with up there. So if you shift k by a reciprocal lattice vector g, you get back exactly the same wave function, which was what we were trying to answer in the first place. Is it special that when you shift k by a reciprocal lattice vector, you get back exactly the same wave function? Is that special to the tight binding model? It's not. It's a property of the Schrodinger equation and periodic potential. Okay? All right. So the implications of this theorem, which is viewed as so important, is one, implications. One, an excitation, all excitations can be described. All excitations can be described in one Brouillon zone, in one BZ. Because whenever you go outside of the Brouillon zone, you can just shift by a reciprocal lattice vector to get back into the first, back into that Brouillon zone. So that's an important statement. Second important statement, maybe more important, is that a periodic potential does not change, does not scatter crystal momentum. And this is something that I mentioned before when we discussed the tight binding model, that the crystal momentum is conserved. Crystal momentum is always conserved, and the fact that we have this very strong periodic potential doesn't ruin that. The reason this is so important, remember we had this puzzle when we studied the Sommerfeld model, that you have this mean free path of electrons, which is enormously long, hundreds of atoms or thousands of atoms long, and we couldn't understand it because there's a big nucleus that the atom can hit every few angstroms. It could scatter off of tons and tons of nuclei. The point here is that you don't have pure plane waves. What you have is modified plane waves. You have these plane waves times a periodic function. But once you modify the plane wave by multiplying it by this periodic function, then it's perfectly good plane wave to go all the way across the system without scattering at all. So if you take an electron, you put it in a little wave packet of this modified plane wave, it would travel clear across the system as long as it doesn't hit any impurities or nasty things like that. But it could go all the way across the system without scattering at all. So this sort of resolves our initial issue of why it is that electrons can travel so far without scattering. Okay, and where did this result come from? It's important to realize that this important result really came from Lowey's condition. It came from the fact that a periodic potential only scatters you by reciprocal wave vectors. All right, so the one thing that this doesn't do for us is it does not manage to help us actually solve the Schrodinger equation. So solving Schrodinger equation is still hard. And we've already discussed one way to do it. One way to do it is tight binding. And by tight binding, what we're really doing is we start with atomic orbitals, and allow weak hopping. But that might sound a little non-generic because maybe the hopping is strong from one place to another. So it's useful to, it's actually very useful to think about it from a very complementary viewpoint, where instead of starting with a tight binding model, we start with plane waves. Start with plane waves. Plane waves. And add weak periodic potential. V of r. So it's entirely the opposite way of looking at things. This approach, approach 2, 2 is known as the nearly free electron model. Nearly free electron model. And it's a very useful model for understanding a lot of the physics of semiconductors and band structure in solids. So let's go about that. Let's start it. We probably won't finish it today. But so how do we do this? We start with our H0 on K, our plane waves, without the periodic potential. So E0K on K, where E0 is the usual h bar squared K squared over 2m. It's a good place to start. And then let's assume V is weak. Assume weak V. All right, so what do you do when you have a weak perturbation to a Hamiltonian? Well, you use perturbation theory, which you presumably learned last year. So you remember what happens to the energies in perturbation theory. So let's start with first order perturbation theory. First order pert. The energy, this will probably look familiar. The energy of the wave, the eigenstate k, is the bare energy without the perturbation plus the first order perturbation theory term, which is k v k. And this matrix element here, well, I scrolled it off the top of the board. No, maybe I didn't. Maybe I did. I think I did. We defined it as v sub 0 because k minus k is 0. And this v sub 0 is the same for all k, So this just gives an overall constant energy shift of the eigenstates. So the eigenstates either get shifted up in energy or they get shifted down in energy. This is sort of the zeroth Fourier mode of this potential. It's whatever constant potential is added on top of any fluctuating potentials, things that change in space. So the zeroth Fourier mode of the potential just shifts up and down the overall energy of k. Does this expression look familiar? First order perturbation theory, you just take the exponent? Yeah, okay. Good. So this is not interesting, and as a matter of fact, people frequently drop V0 because it's so uninteresting they just get rid of it. I'll try to keep it, but maybe I'll forget it by mistake at some point. So second order is more interesting. So at second order, you have Ek equals Ek naught, that's the bare piece, plus V0, that's the first order piece. And then you have the second order piece, which is sum of k prime not equal to k. Then we have k prime v k squared over e sub k naught minus e k prime naught. Is that the right order? Yeah. Does that look familiar from second order perturbation theory? Good. All right. Now, what do we know about this second order term? Well, again, we have Lowey's condition for the upstairs matrix element, that in order for that matrix element to be non-zero, you must have k prime minus k must equal a reciprocal lattice vector g. So this term here can be rewritten as sum over g of reciprocal lattice vectors g of v sub g squared, where g is k prime minus k, divided by e sub k naught minus e sub k plus g naught. Good? Look happy with that? Somewhat? Okay. So this is our expression for the second order shift in energy of the plane waves that we started with. But we have to be a little bit careful about expressions that look like this. And the reason we have to be careful is because you might have a situation where the two terms in the denominator are either equal to each other, in which case you get 0 downstairs, or very close to each other, in which case you get something very small downstairs. And in either case, the second order term would blow up, in which case you have a divergence. And that means the second order perturbation theory is not correct. So you must be careful careful when E sub k, let's just write it as E sub k naught is approximately equal to E sub k plus g naught. Now, when does that happen? Well, E sub k is actually just proportional to k squared, so that will happen when absolute k equals absolute k plus g. Well, where's that? You'll remember somewhere here, there it is. It's the condition for being on a Broughton zone boundary. When you're on a Broughton zone boundary, E sub k and E sub k plus g are actually the same. Let's actually draw a picture of that. So what we have is we have a, this is our Baire spectrum, k and E. The Baire spectrum is just a parabola. So this is E sub k is h bar squared naught k squared over 2m. And here's pi over a. Here's minus pi over a. And the energy of these two, these are separated by a reciprocal lattice vector, 2 pi over a. And their energy is identical. So this would give us a divergence in second-order perturbation theory. Similarly, if we go to minus 2 pi over a and 2 pi over a, these are separated by a reciprocal lattice vector, 4 pi over a, and their energies are identical. So they will give you a divergence in second-order perturbation theory. So the place where second-order perturbation theory fails is exactly when you're on a Broughton zone boundary. So what we're going to need to do is we are going to need to, we're probably going to have to do this next time, but what we're going to do to fix this problem, by using degenerate perturbation theory. Degenerate perturbation theory. Which hopefully you've learned something about already. So we're not going to have time to launch into that today, so I'm going to actually take the opportunity to insert one piece of information, or maybe two pieces of information about scattering that I promised you we would talk about sometime. And that is scattering off of, so maybe I'll put that over here, scattering off of X-rays and neutron scattering, X-ray and neutron scattering. This is a different subject, just inserted in this last 5 minutes. Neutron scattering from liquids and amorphous solids. So in liquids and amorphous solids, we do not have periodic structures. We do not have periodic arrangement of atoms. But nonetheless, you get a lot of information out of the neutron and X-ray scattering. If you think way back to when we did Fermi's golden rule, that the scattering amplitude is still the Fourier transform of the potential, but it's not a periodic potential. It's Fourier transform of the non-periodic potential. But does that mean there's no information in it? No, there's still information in it. It's just that you don't get sharp peaks anymore. What you get is, here, there it is. So this is X-ray scattering on liquid aluminum. It's heated up to some high temperature, so it's a liquid. There's a function of the scattering angle, or the reciprocal wave vector, that's the wave vector along this axis. The amplitude of scattering has peaks. And the peaks represent roughly the distance between atoms. It's 1 over the distance between atoms, the same way the peaks represent the periodicity of the unit cell when it becomes crystalline. Now what happens is, as you cool down a liquid and it gets more and more crystalline, there becomes more and more local order, and these peaks get sharper and sharper and sharper. And finally, when the thing actually crystallizes, they become delta function peaks, the way we expected them to for a crystal. But if it's a liquid, it's sort of, you can sort of think of a liquid as locally being like a solid. You know, each atom has a couple neighbors, but if you sort of look farther away, it's not ordered anymore. It sort of loses its order. But if you sort of look just in some small region, it probably has, you know, it's organized over a small region. So you get these sort of broad peaks in the scattering spectrum. Okay, I think maybe I won't try to cover any further issues today. And we'll start again on Wednesday, I think. Have a good weekend.